Okay, in this video we're going to be determining domain of a function just from its equation. So we're not going to be seeing these graphed at all, but if you ever want to graph something just to see what the function looks like, feel free to put it into your calculator and graph it. All right, so what is domain? Domain is basically what x can be, what we can plug into the function and it'll run smoothly. A lot of functions, the domain is just all real numbers. Anything works. But sometimes we do have restrictions on our domain. What does that mean? A restriction means that, hey, you can't plug this number in. So, some domain restrictions are if you have a 0 in your denominator. If some value of x will make your denominator equal to 0, it's not going to work. We cannot divide by 0. In an even root, like just a square root or a fourth root, we cannot have negative values under there. So in this case, if you were to plug in 1 as an x value, you'd have 1 minus 2. You'd have a negative 1 under your root. 1 would not be a part of this domain. So I know I said domain is what x can be. However, since there are an infinite amount of numbers out there in the real number system, what we do is we say, hey, x can be everything but this one number. So it's a lot easier to find the domain by just seeing what few values don't work and then excluding them from the all reals. Okay, let's start with these first two examples. We're going to find our domain and we're going to write it in interval notation. If you do not know what interval notation is, check out the previous video in 1.7 called Set Builder and Interval Notation. All right, so our red example here, we see that we have a fraction. This immediately sends up a red flag because we have the potential for our denominator to equal 0, which is one of those two main restrictions in our domain. So whatever x value makes this denominator 0 cannot be in our domain. So what we're going to do, like I said previously, is figure out what value or values of x don't work, and then we're just going to exclude them from our domain. So let's take a look at the denominator. We're going to set the denominator to 0. Why? Because I want to see what makes that denominator 0. Then we're going to say x cannot be that number. When we solve, we'll see that x is negative 1/3. Now sometimes people will write like can't equal. It doesn't really matter. This is just like scrap work for you off to the side to figure out what the domain is. All right, so basically x cannot be negative 1/3 because that makes the denominator 0 if you were to plug it in. That's the only value of x that won't work here. All other values of x give us non-zero values, and therefore they're totally fine for the denominator. How about the numerator? What if you plugged in 2? You'd have 0 in the numerator, and you'd have 7 in the denominator. That's totally fine. 0 in a numerator is great. It's okay. It just means we equal 0. 0 in a denominator is not okay. Therefore, our domain here of f of x is all real numbers except negative 1/3. Well, how are we going to write that in interval notation? Basically, we're going to say that, hey, our domain can start all the way down at negative infinity, but once we hit negative 1/3, we're not okay. So we cannot equal negative 1/3. But then we can jump over negative 1/3, and we can travel all the way to positive infinity and be okay. That is how we write our domain in interval notation. We're excluding this one value by sort of hopping over it, and we're traveling all the way from negative infinity to positive infinity with this one bump in the road that we're skipping. This U in here means union. It's just a way to join two like intervals for our final answer. Okay, our second problem here in blue, g of x, we take a look and see, yes, we have a fraction again. So there's potential that our denominator could be 0 and we might have an issue. However, there's no x in our denominator. Our denominator here is always, always, always 7. It does not matter what the numerator is so long as the denominator is not 0. There is no value of x that when we would plug into this function would make this denominator 0. Therefore, we have no restrictions on our domain. Our domain does not hit any bumps in the road. Our domain is all real numbers, and that's how we write that in interval notation. Okay, these next two examples both are square roots, and therefore that's our other type of restriction. We cannot have a negative value under the root. The value under the root is called the discriminant. So here our discriminant's 2 minus x. We have to make sure that 2 minus x yields a positive answer or is 0. What we're doing here is, because we can only have 0 or greater under here, we can't have negatives, we have to force that to work. So we are forcing the discriminant to be what we want. Therefore, we'll see what x has to be at the end. All right, let's solve this inequality. So we're going to subtract 2 from both sides. And then I'm going to divide by this -1 that is in front of the x here. Remember, when we divide or multiply both sides of an inequality by a negative, we must flip the sign. Therefore, x has to be less than or equal to 2. If you are not convinced of that, plug in a couple numbers. Plug in 2. That works. We'll get 0 under here. Plug in another number less than 2. Let's plug in 0. 2 minus 0. That's fine. We have a positive number under the root. So this is our answer. However, we want to write it in interval notation. So to write this in interval notation, we say, hey, since x is less than or equal to, we can start all the way down at -infinity and go all the way up to 2 and equal to. That's our domain. In number 4, we also have a square root. Once more, we need to force what's under that root to be a positive number, or it can be 0. That's okay. It just can't be negative. And then some of you might look at this and say, well, this will never be negative, will it? No matter what, when we square something, it's 0 or positive. And then you're adding 1. You're always going to have a positive number under there. That's true. Let's just do that algebraically and make sure that it works. So we're going to have x squared is greater than or equal to -1. Then I'm going to take the square root of both sides, and here is our issue, right? Right here is the issue, because in the real number system we can't take the square root of a negative. Therefore, there's no issues with this. It's always 0 or greater. Therefore, we do not have any restrictions on our domain. No number, if we plug it in for x, will give us a negative under here. So we say that our domain has no restrictions. Our domain is from -infinity all the way to +infinity. We write it that way because that is interval notation. Okay, our last example, number 5, does not look like it has any potential restrictions, right? So from the very beginning, we said those restrictions are, hey, if there's a fraction, there's potential to be an issue in the denominator if it equals 0. If we have a square root, there's potential for an issue if there could be a negative under that root. Well, we do not have a fraction. We do not have a square root. X can be anything we want it to be. There's no issues. So in this case, this is just a nice polynomial. Our domain is all real numbers. No issues. Okay, I want you to try these next two. A is a little bit more challenging. As you can see in the denominator, there's an x squared, so there's potential for this to equal 0 2 times. So just be careful. And then in part B, try that one as well on your own. I'm going to pause, and then you'll see the solutions here in just a moment. Okay, the solutions are over here. So for this top one, if you set 4 minus x squared equal to 0, you'll end up taking the square root of 4, which will give you +2 and -2. Don't forget your plus or minus. Therefore, that 2 and -2 will both make this denominator 0. If you're not convinced, plug them in. They do. You'll get 4 minus 4. So we have two issues. We have to skip over both -2 and +2. Therefore, we can travel from -infinity to -2, jump over -2, travel up to 2, jump over 2, and keep going towards infinity. So however many restrictions you have, in this case we have 2, you'll have 3 intervals, so you'll have one more interval than the amount of restrictions there. Okay, so let's take a look at part B. P of x is 3 plus x, square root of 3 plus x, and that ends up being our domain.